Hi, welcome. So exam 1 is going to be next, check the right date, February 3rd, so Monday. Person. So it's in person upstairs in the Ingman lab. Make sure that you have lab access if you haven't yet for the CADE lab access. So do check that you have that. If you want to go up to the labs, log in just to make sure you do have that. If you've been in from our labs, I think you should have already applied for them, but if not, just double check that you have that. So check that you have CADE lab access. Otherwise, it's going to take it's like a 15-minute process to get that while you're in there. So you want to make sure you have that before you start the exam. So do double check that you have the CADE lab access, and then also locate the room so you know exactly where to go for next Monday. All right. Any questions about the upcoming exam? So the other voltage, current, power. So the concepts of voltage, current, power, concepts. Voltage, current, power, and then nodes, extraordinary and ordinary, branches and loops. So making sure you understand those concepts, and then being able to apply KVL, KCL, Ohm's law. So those are applications, being able to apply the power equation. So those are all techniques, and then the memorization of the Ohm's law and the power equations, being able to calculate equivalent resistances, voltage and current dividers. Yes.
You said this is like open node.
Yes. So correct. So open notes, open iPad. What you cannot use and would be considered cheating is to use things like a chat GPT or a any AI type of help on the exam. So it needs to be your own work. Anything that's used from that would be considered cheating. Using an online tutor, online assistance from another individual, or artificial intelligence assistance would be considered cheating. Yep. So if you have my notes on an iPad electronically, that's fine. I'm going to ask everyone to keep on their screen all of those electronics so that you can, anything open that you can see so that one individual can look at it. So no multi-tab browsers, just one browser open with one tab on it, and then tiled in the windows so that it's very visible to be seen. So that will be the request. And then online calculators are okay with me. MATLAB's okay to use also if you would like. Just not a circuit simulator would be the other one. So anything that's doing the work for you, such as a circuit simulator, would be the only other thing. Is that clear? Okay. All right, so concepts are listed here. We've gone through all these, and we'll continue to do review today and then review on Friday. So after today's lecture and problems that we work through, please let me know what other content you want me to go over additionally, and then I'll prepare notes for lecture on Friday. Okay. All right, any other questions about the upcoming exam, content? Yes?
Are you going to post like a previous exam one or whatever?
So what is in the Unit 1 practice problems are previous exam questions. So those are good practice, is those Unit 1 practice problems. So those will be examples. They're a combination of some homework and then some of the previous exam questions. So they get moved into there with the solutions so you can check.
Is the CADE lab access just the paper we filled out to get into our lab room?
No, so the CADE access is a little different. So you actually, do need to, let me see if they have the information. Maybe access login, University of Utah. Okay, so, go here. So if you click on this link, the usertools.eng.utah.edu, it will bring you up to this page. So if you can try your CADE username and your password there, these would be the same. It's supposed to be the same, but not always works, as your one if you set it correctly for our ECE 1245 and 1050 labs in there. So they should be the same if you click the right button, but some of you may not have and may have different logins. So you can log in here, see if it works. If not, down at the bottom there's a create a CADE account. And so you would go to this and go through the submission process to get that done before Monday. So do double check, and then if not, create your own. There is a setting in there at some point that you can link our lab computers with the CADE CADE with the University of Utah one, I think. So all of them can be together. But if it's not clicked and you don't know, then double check that it's there. Okay. All right, any other questions? Yes.
The test itself, will it be digital or will it be on?
So it's gonna be digital. You need to submit your work to get credit for it. So you are gonna write and then submit your work. The answers that are, so it's gonna be very similar to your quizzes where you've taken the quiz and then you put an answer. It will tell you it's right or wrong. It doesn't give you any partial credit, and then they'll be graded for partial credit.
Your iPad, like the work for it?
Uh-huh.
Or,
Yep. Yep, so just like before, you can do it on your iPad and then submit it through your iPad. So do bring whatever you've used in the past to scan. If you've used a home scanner to scan your work, there is some scanners in the lab that you can use to scan your work at the end if you need that. Otherwise, bring your phone if you've been doing it on your phone, iPads, tablets, whatever other device you've been using to upload your work for the quizzes. Okay, other questions? Clarifications? You guys are all ready, right? Just need to study a little more? Okay, all right, good. All right, so let us look at this one. So first, let's find plus, minus. I'm going to call this V1, the voltage that goes across this resistor here. And then we're going to find do it this way. Plus, minus, I'm going to call this V2. So first find V1 and then work to find V2. And let me put in a ground. I'm putting the ground in over there, which I know is a little bit weird, but this first one will be easier. Okay, good job for those that found the polarity correctly. I did want to talk, well, first, let me solve this, and then we'll talk about the polarities. So, you can notice that this is a voltage divider because you notice that this node is the same, and then you have ground on this side of it. So across those 3 ohms, you know the voltage here, which is 4 volts. So if I'm measuring that node, that's going to be a plus to ground is going to be plus 4 volts. So that's also the polarity between these two. I have 4 volts on the right and 0 on the left, so it's voltage across resistances, and that could be a voltage divider. If I notice that, then I could say that this is V1 is equal to a minus, or 4 times 3 over 6, and then I have to decide is it plus or minus. So with that, you can see that the sign closest to the blue is a negative, and the sign closest to the 4 is a plus. So because these two are opposite, that will be a negative here. So that will give me a negative 2 volts. The other way to do this, if you're like, oh, I didn't notice it was an actual voltage divider, is that you could do a KVL loop, and you would label the current whichever direction you want. I'm going to label it the same direction as this was already labeled, so plus to minus going in this direction. So as I take my loop, I'm going to go in this direction around the loop, so I'm going to go a plus, plus, plus. So that would be plus 4, plus I times 3, plus I times 3 equals 0 is my loop. Solving for I get a minus 4 over 6, or minus 2/3. So now it's going to be these polarities are the same, plus and minus and minus. So my V1 is going to be a plus I times R, which is 3 in this case. So minus 2 over 3 times 3 for minus 2 volts. So either method is going to give me the same value. So one was taking KVL loop, solving for I, and then the other was to find use the voltage divider. All right, finding V2 here. Is the same way. You can see that it's another voltage divider. So then you would do the polarity on this one is that the plus is the closest to the blue, and the plus is the closest here, so they're the same polarity. So for V2, you have a plus 4 times 6 over 12. 24 over 12 for 2 volts. Sorry, 2 volts. Or you can take a loop and define the current direction. If I define the current direction this way, notice that I have a plus minus, which is going to be opposite each other for the I and the V. So then my V2 here would be a minus whatever I find for, I'll call it I1 or I2. I'll do I2s. Minus I2 times 6. And then my loop, if I go around this direction for my loop, I have a minus, and then a minus, oh, sorry, wrong minus. Minus, and then this would be a minus. for a minus I2 times 6 minus I2 times 6 minus 4 equals 0. So this gives me I2 is a minus 4 over 12 for minus 1/3. Wait, minus, and then V2 is a minus 1 over 3 times 6 for positive 2 volts. So this is the voltage divider, and then this is using KVL and Ohm's law. All right, questions? Yes.
For the KVL loop for I2,
Uh-huh.
did you pick the direction of the current, or did you?
I did both. So I picked the direction of the current arbitrarily.
You could have done either way?
I could have done it either way. So I wanted to show you opposite what I had chosen before. So before I chose it with the green one, I chose it the same direction as what was labeled, so I knew that I had a positive I times R. So when they're the same polarities, plus on the left, negative on the right, they'll be plus IR, or yeah, I times R is V. And then when they're opposite, which is the case in the second one, you'll have to do a negative I times R. Okay. All right, so let's talk a little bit about the polarities. So if this is my V1, I notice that on the node that's closest to V1, this is going to give me a plus, maybe orange. This polarity that's closest is going to be a negative. This polarity that's closest is a positive. I'm going to do a different one. This polarity on V4 is going to be a negative. And this one is also a positive. So if I do a voltage divider, what polarity should V1 be? Plus or minus? This will be a minus polarity. V2 plus, V3, V4, that one would be minus. So even though it's not right next to it, it's the sign closest to the node where you know the voltage. Does that make sense? Yes.
When you were figuring out V1, when you go up to where you use the KV,
Uh-huh.
so you did 4 plus I times 3 plus I times 3. How do you know whether or not you should add or minus the second I times 3? Because the voltage wasn't labeled, its polarity wasn't labeled.
So it just depends on which direction I label that. So I did label it going left to right, and so that's the plus. Get a different color here. That's the plus to minus.
What if you label it the other way? What would that look like?
So if I labeled it, let me do it down here. So say I labeled it this direction.
No, so the first one, so does the second one always have to go the same direction as the first one?
Oh, in the branch. So you have to notice that's a branch. They're connected by an ordinary node. So yes, the currents are going to be the same in the same direction
And what you, okay.
because it's one branch.
Yeah, the current goes in the same direction, but the voltages also have to go in the same direction just because it's one branch.
So you may not know like what the voltage is across an element. So you can label that one arbitrarily. You just have to decide. So this one was already labeled for you as plus to minus direction this way. That was given. So then your choice is the current. So if I chose to label it in this direction, then when I take my loop, it would be, if I go in this direction, it would be a plus, and then a minus, and then a minus.
But the other 3 ohm resistor, its voltage is also the same opposite direction, just cause it's the same branch, you know it has to be that way, or?
So say I label this, I'll call it V6 because I labeled all the other ones. So say I labeled it this way. V6 here would then depend on what the labeling is for I1. And then when I do Ohm's law for that, V6 here is going to be a negative because these are the same. Sorry, will be plus because they're the same. So I1 times 3 there.
And then in your KVL, would it be 4 minus I1 times 3 plus I1 times 3, or?
No, you would still do it with the current direction. Because you're solving it for current. It's only when you do the Ohm's law do you determine what the polarity is for the Ohm's law. So here I would solve this. This gives me that I1 is equal to 4/6, or 2/3. And it's a plus this time. So then when I plug it in for V6, I'm going to get a plus 2 volts. But when I plug it in for this V1, this is going to be a negative because they're opposite. So this will be a negative I1 times 3.
So when you're doing a KVL loop and you're solving for I, you only care about the direction of I in that case?
Correct.
But so what you're solving for is what direction matters? Or I guess it's different every time? Because
So-
sometimes it's if they don't line up and sometimes it's just the direction.
So when you take a loop, you can do it either with the currents in there or with the voltages in there. So if I did a loop, say I did do the loop with the voltages instead, this would be a plus 4 plus V1 minus V6 equals 0. But then writing V1, I have to write it opposite because the plus and minuses are opposite there.
Okay.
So then this V1 is a minus I1 times 3. And then V6 is the same, so then I would write V6 is a plus I1 3. Does that make more sense?
Yeah, I guess I don't know how to know, because when you do the currents, it's 4 minus I1 times 3 minus I1 times 3. But it's just weird to me because the voltages are, one of them's flipped and one of them's not. So it's just weird that you subtract both of them too.
You just have to be clear, like, am I using voltage in this loop? Write it with all voltages as far as the variable voltages. And then when you substitute in, you need to make sure your Ohm's law is the correct polarity based on the labeling of the current and the voltage. So that's why you need to make sure you've labeled them
Okay.
in there so you know, like it's clear to you, like, yes, the labeling is this direction, that polarity is the plus and minus on those. Otherwise, yes, it gets confusing and don't keep it in your head. So definitely write it down and then double check when you've done it. Go back and check and say, okay, I circled the green as plus, plus, minus, and yes, my plus, plus, minus. But then I did the other equation in red, so then I went through and looked at those, and that was a plus, minus, minus, which is also that. So whichever way you write it, and then as you're writing Ohm's law, you double check the signs. Like for V6, oh, those are the same direction, or the same polarities on each side. So a plus IR. Oh, across V1 there, they're opposite.
Yeah.
So
I
I'm
guess
gonna
you
write that as a negative.
I guess you just think about it like, when you're doing this, you're just calculating the voltages without worrying about the directions yet. And then when you do just the voltages, that's when you add the directions, I guess.
Whatever you wanna say in your mind to wrap your head around it. everybody's gonna say it differently, so I've tried to explain it in different ways, so hopefully that will make sense. Yes,
So if the sign, what you were saying is if the sign closest to the node where we know the voltage is, if it matches, it's positive, if it's different, it's negative?
so it also depends, just like I did, the direction you label your current when you're solving too. So it does depend on both. But if you are doing like the current divider, or I mean the voltage divider, it is assumed that the direction of the current was the same as the labeling of the voltage here. So when we went and solved that equation, so that's where you can just look at it by inspection and say the closest ones if you're using the voltage divider. And then it is good to check, like at the end, you should end up with these as a negative compared to V1 or positive compared to V1. So that's another thing to be able to check. Yes.
So I guess I'm just a little confused. How do you assign the polarity to the resistors?
So if it's labeled, it's already
Yeah.
like assigned, and then you can choose which direction you want to label the currents. If
Okay.
it's not labeled, then you can also choose the direction of the voltage. And then you
Okay.
solve that circuit, and then
Just for
you're,
how you label it.
however you've labeled it.
Okay.
You just stick with that labeling, don't
Yeah.
change it.
Okay, sweet. So
Okay.
does it have to be then consistent in the same circuit, or is it?
So it does need to, like, once you've labeled it, solve every variable in that circuit with it the same labeling.
Okay.
Don't change.
Okay.
Okay. All right. I think I saw another hand. Was there additional question?
I just have a question about like the R total. So for the voltage divider,
Sorry, just a second. Thank you. Ask your question again, please.
so I just wondered like with the R total, like I know there's like for voltage dividers, there's like a wire with like resistors and series in between circuits.
Uh-huh.
I was wondering like if there like isn't one there, but the R total in that case just be all of the resistors added together, or how do you tell
Uh-huh.
if it's like there's gonna be like multiple, I guess.
Okay. So the question, if you didn't hear all of that, was the R total that you have on the bottom of the voltage divider, correct? So how do you know which terms to put into that R total? So it's going to determine it by whatever's in the branch. So if you have multiple, like if you have 4 resistors there, your R total would be added up all of those resistances. So you would have 4 terms added up in the bottom for R total. So in the voltage divider, right down here. Okay, so voltage divider. A little dyslexic today, I think. Divider, there we go. Voltage divider, the R total on the bottom. So this R total is a summation of all resistances in branch. So whatever is in that branch. So if you have 6 of them, there's going to be 6 added resistors there. And remember that the voltage divider is just the voltage across a resistance. So it's not, if I do something like this, this is R1, R2, R3, R4, R5. For example, if I would do V4, it's only the voltage between that top and bottom of that R4. So if you needed to find like the voltage here, I'll call it Vy. And I grounded my ground here. To find Vy, I would have to add up the voltage across R5, voltage across R4, the voltage across R3 to give me the voltage at Vy. Or I could do the other direction, and it would be V1 minus the voltage across R1 minus the voltage across R2. So that said, this was the direction of what polarities I was saying there. So say, let me do this one. Okay, so say I did this. V1 would be a positive. V2 is going to be positive here. V3 is going to be positive here. V4 is going to be positive. What is V5 going to be? It's going to be a negative. So Vy would be the summation from ground of those three. So it would be a minus V5, which is also going to be negative. So if I had actually labeled the polarity the other way, it would be a plus. And then plus V4 plus V3. Or I could say Vy is V1. So it would go, I'll do this different color. Green. Plus V1 minus V1 minus V2. So either of those pathways, so basically it's the pathway here or the pathway here from ground. Hopefully that made sense. Yes.
So in the situation of voltage resistors, you have to find the voltage across the resistor before that point in relation to the ground.
Say that again.
So
Sorry.
if you're going from the ground up
Uh-huh.
to Vy, you just have to find the voltage resistance across R3 technically.
Nope, that's only going to be the location right here. That's only going to give you voltage measured right there between those two nodes. To get Vy, which is going to compare it all the way to ground, you would actually have to add up all three of those voltages for that one. So if I took my multimeter, actually plugged that in, that's measuring from whatever node I put it in to ground. So it's all three of those voltages added, not just the one across R3.
So you would have to do a voltage resistor for each one and then add the totals of those
Correct.
to find that.
Or you could sum them all up as one resistance and then take it across that one equivalent resistance. Because now combining them would combine them and give you the location from that point to ground as far as an equivalent resistance. Does that make sense? Okay, yes.
Okay, so I'm clear on the point that V5 will be, if you're going clockwise in this series circuit, that V5 will be negative, V4, 3, 2, and 1 will be positive. But how does that manifest when I plug them into the voltage divider equation? Do I just set up negative V5 equals V total times your resistances?
Yep, so V5 here would be a negative V1 times whatever R5 over R1, 2, 3, 4, 5.
Negative V1 being your total, the battery.
Yep,
Okay.
does that make sense?
Total sense.
Okay, other questions, yes.
Okay, so I guess we assume that positive voltages flow out, the positive side of the voltage source, right?
Uh-huh.
It's right from negative to positive. So if we're given a problem and it says like negative 4 volts, do we assume that's flowing out the negative side or out the positive?
So you treat it just the same, so it's still gonna go out of the positive side.
It's still going out of the positive.
And then if it's labeled, great. If not, then you get to pick. And again, you could be wrong if you arbitrarily put it in there and then you solve it and you'll find that it will be a negative value. Again, that just means it's flowing in the other way. So keep it same, just keep them the same. So keep flowing it out of it typically,
Okay. So,
even though it's a
so
negative value.
Even if we're given a problem and it says negative, we're still assuming it's flowing out of the positive
Yeah.
side? Okay, and then, that makes sense.
Because that way it will just keep it always consistent.
Okay.
All right, yes.
So if we do get a negative, do we wanna swap our notation to show it or no?
Nope, keep it there. Just if you don't like the negative number, just put a variable there and then substitute it in the math later.
Okay.
All right, yes.
But adding up our REQ, going back to that example I was talking about,
Yep.
It'll
Yeah.
always be, you always just add up the values,
Yep.
there's no negatives.
Yep, so I guess this would be a case though, so let me give a different example. What if you had this? Okay, I think this was probably similar to something in the homework or quiz. So if you have this, you would first have to combine these two in parallel as your resistance that you are adding up, because you need it all in one branch. So say I wanted to find V1 here, and then I'll label this one V, I guess I'll call it 4 here. V4 there. So using the voltage divider, V1 will be what? Plus or minus first off?
Positive.
Okay, good. Positive V1 X.
So this is Vx times R1 over this REQ.
And REQ would be R1 plus R2 in parallel.
Right. 1 over R2 plus 1 over R3.
Can't write today. Plus R4. So it would be that one. Sorry. Here we go. Head out of the way. Does that make sense? And then V4.
Before would be negative Vx times R4 over a summation.
Correct. So negative Vx instead, R4 over. Okay, is that more clear? Okay.
So I guess for V4, do we assume that that one has the opposite of negative because it's close to ground and it has to zero out? Is that why we
Yeah.
assume it has the opposite polarity as opposed to R1 and R2, R3?
Yeah, so you can either do that node is the closest, or whichever. You're kind of looking at either side of the battery. And in this case, this is a closer location to this one. So it's going to be that there's a plus closest and this has a negative closest. So they're opposite, so it will be a negative. The other way to think about it is you're from ground, you're looking at adding up all of the resistances to equal the battery. So in order to add them up, if it's plus on the top to minus, it has to be plus on the top of each of those as you add them up. So visually, if you look at it that way, you could also determine if it's plus or minus. Some people don't visually see it, so that's why I describe also to think about it as the node that's closest to it. Are those the same polarities or are they opposite? If they're the same polarities in the nodes that are closest to them, it would be plus. If they're opposite, negative. In this case, they're negative, or opposite, so a negative.
I think that makes sense.
Okay. All right, I think I saw a couple hands.
Okay. So you said if there's two negatives, it makes it positive. So if V4 had like the inverse polarity, would it be a positive voltage?
If Vx was a negative, so say it was -4, it would be a -4 and end up being a positive value, yes.
Well, I mean, okay, so with your diagram, right? You have
Yep.
V4 as the closest polarities for V4 is the negative voltage on Vx.
Uh-huh.
If V4 were swapped and it was negative on the bottom, would that be a positive voltage?
Yeah.
Okay.
Yeah. So if I called this V5, V5 is going to be a positive voltage.
Okay.
All right, yes.
What if you wanted to find a voltage drop across like R3?
Okay, that was gonna be my next one, so good question. So, somebody tell me polarity on the top arbitrarily. Okay, if it was positive to negative, and I called this V3, note that V3 is also across V2. Maybe I'll call it V23. Call it 2-3. So that's across both of those. So then V23, is it going to be positive or negative? Okay, good. So it's going to be positive, and then it's going to be the equivalent of those two.
So does it, oh, it doesn't matter. The voltage drop is the same. It doesn't even matter if the resistances are different, right?
Correct.
It just doesn't add up anyways.
Yep. So the voltage will be the same, but then they're two different branches, so the currents going through them are going to be different. So the values of them is going to determine the resistance, difference in resistance values is going to determine which current flows where. Does that make sense?
How did you do the voltage divider equation right there?
So it's Vx across both of those in parallel. So this is the parallel, R2 in parallel with R3. And then the total is R1 plus those two in parallel plus R3 or R4. Okay, is there another question? Yes? You're stretching again? Oh, okay.
So basically, it doesn't matter, like that, them being parallel or them being one resistor, the voltage drop is the same no matter what, right?
Correct.
Okay.
Yep, so the voltage across that location is the same. So that goes back to the concept of one voltage across parallel branches.
Yeah.
All right, is there a request for types of problems on Friday? Yes. Current dividers? Okay, current dividers. Other requests? Yes. More of this polarities? Okay. Okay, so voltages in the circuit. Yeah, just one second. Yes, Dylan? Okay, sounds good. All right, yes, questions?
Polarity only ever like talking about so again, your negative and positive should never really mess with the numbers.
Correct. Yep. 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 So the magnitude will stay the same. It's the polarity of it will be different.